Let us now examine the notion of ideal parallelism. You've learned about computation graphs, and now I'll just show you a graph without showing the program. So we have S1, S2, S3, S4, S5, and S6, let's say, and an S7 that waits for all of them. And let's assume some execution times over here. Let's say this is 1, 1, 10, 1, 1, 1, 10. So what we've already learned is that the amount of work in this computation graph would be the sum of the execution times, which would be 3, 10, 13, 24, 25. So the work is 25. And the critical path length is the length of the longest path. So we look through this. It's not this one because S4 and S5 are small. It's not S6. It's the one that goes from S1 to S2 to S3 to S7. And that adds up to 2, 10, and 13. So what we refer to as the ideal parallelism is the ratio of these two numbers, work divided by critical path length, and that's the ideal parallelism. And the reason is that no matter how many processors we have in our parallel machine, this is the factor by which we can, in the best case, expect the program to run faster with parallelism. So over here, we see it's 25 by 13, and that's just under a factor of 2. So no matter how many processors we throw at this computation graph, we cannot expect to do more than 2 times faster than the sequential case. Now let's look at an example to illustrate this concept of ideal parallelism. The example I want to use is of string search. Imagine that you have a string of characters, and the length of the string is n, and the characters could be something like A, B, C, A, B, B, A, C, and so on. And what we want to do is we want to look for a certain pattern. So the length of the pattern is M, and let's say the pattern is BC, and here's one occurrence, and there could be many more in the string. If we wanted to write a sequential algorithm to determine if the pattern exists in the string, we would write something like this. We would say for I 0 to n minus m, and what we would want to do is compare the string S starting from I to the length of the pattern and ask, is that equal to the pattern? So, and if this condition is true, we would normally set a Boolean variable like found to true. And let's assume that found was false in the beginning. And now we can return the value of found to let us know if an occurrence was found. And notice this works even if there are multiple occurrences of the patterns. We're just going to go to the whole string, and we might assign found equals true multiple times, but we'll return true if there's at least one occurrence. This is a very important application in practice. It's used in computational biology. It's used in web search applications. So an important question is, can we use parallelism to make this go faster? So if you use the notations we've learned, one observation is checking the occurrence of the pattern at different starting points can all be done in parallel. So we could put an async over here, and we need to wait for all the iterations to finish before we can determine whether we found an occurrence. So we can put a finish over here, and that would be scoped over here before we return the value of found. Now let's reason about the ideal parallelism in this algorithm. The total amount of work for this algorithm is, and let's assume that n is much larger than m. So I'll do some approximations in the estimation. So the total amount of work is you have n minus m iterations, which are approximately n iterations of the I loop. And for each iteration of the I loop, we are comparing a pattern of length m. So the total amount of work is n times m. And we can figure this out without even drawing the computation graph. We're just looking at the work going on. For the critical path length, well, the way to do it would be to draw the computation graph, but we can reason about it. And looking at the async, the idea is that each iteration can run in parallel with the other. So the critical path length is basically the time for a single iteration of the I loop, which is the time needed for one pattern match. And that is really m operations. So the ideal parallelism over here is the work divided by the critical path length, which is n times m divided by m, which is n. Now this is huge. It's much better than our original example because we can have long strings of length on the World Wide Web. It can be lengths of billions of characters, and we have the potential of making the search process go faster by a factor of n, by a factor of 1,000,000 or 1,000,000,000, depending on how many processors we have. So what this illustrates is for a given parallel algorithm, even without bothering about which machine we're going to run it on, we can reason about the computation graph, the work, the critical path length, and the ideal parallelism in the algorithm to give us a feeling for what's the best case improvement we can get with parallel programming.